As I told you before, we will consider various types of flowmetry methods. And one of the most important methods in this field is electromagnetic flowmetry. The electromagnetic flowmeter measures instantaneous pulsatile flow of blood based on Faraday's law of induction that a conductor that moves through a uniform magnetic field or a stationary conductor placed in a varying magnetic field generates EMF, electromagnetic field, on the conductor based on this equation. In this equation, B is the magnetic flux density based on Tesla. L is the length between the electrodes with the unit of meter. And U is instantaneous velocity of blood with unit of meter divided by S. For uniform B and uniform velocity profile U, the induced EMF is this: BLU, the magnetic flux multiplied by the length between electrodes and the instantaneous velocity of blood, where these three components are orthogonal. As you can see, we have a magnetic flux here. We have two electrodes to measure the generated EMF. Also, we have a moving fluid inside our vessel. Flow can be obtained by multiplying the blood velocity U with the vessel cross section A. When an AC magnetic field is used, any flux line cutting the shaped loop induce an undesired transformer voltage. If the vessel's cross-section were a square and the electrodes extended the full length of two possible sides, the flow meter would measure the correct average flow for any flow profile. And the electrodes are small, however, so velocities near them contribute more to the signal than to velocities farther away. This figure, figure 8.4 from the book, shows the weighting function that characterizes this effect for circular geometry. These solid lines show the weighting function that represent relative velocity contribution, indicated by numbers of 0.65, 0.85, and 1 to the total induced voltage for electrodes at the top and bottom of the circular cross-section. If the vessel wall extends from the outside circle to the dashed line, the range of the weighting function is reduced. We have a small number of contributions in this circles, in these regions, and when we reduce the measuring of the generated voltage to this dashed line, the range of weighting function is small too. Therefore, we have a better uniform results and contribution based on the velocities of the liquid, the fluid inside this vessel. It shows that the problem is less when the electrodes are located outside the vessel. The discussion means we will locate the electrodes outside the vessel, and the vessel will be located inside in this dash line circle. The instrument measures collectors from a uniform flow profile. For axisymmetric non-uniform flow profiles, such as the parabolic flow profile resulting from laminar flow, the instrument measurement is correctly if U is replaced by U bar, the average flow velocity. Because we usually know the cross-sectional area A of the lumen of the vessel, we can multiply A by U bar to obtain F, the volumetric flow. However, in many locations of blood vessel in the body, such as around the curve of the aorta and near its branch, the velocity profile is asymmetric, so errors result. In previous slides, we considered the main error factor in electromagnetic flow meters, the location of the vessel inside the electromagnetic flux. But we have some other factors can also cause error in electromagnetic flow meters, and we will consider these factors in this slide. Region of high velocity generate higher incremental EMFs than region of low velocity. So circulating currents flow in the transverse plane. These currents cause varying drops in resistance within the conductive blood and surrounding tissues. The second error factor, the ratio of conductivity of the wall of the blood vessel to that of the blood varies with the hematocrit percentage of cell volume to blood volume. So the shunting effect of the wall causes variable error. Also, fluid outside the wall of the vessel has a greater conductivity than the wall, so it shunts the flow signal. The magnetic flux density is not uniform in the transverse plane. This accentuates the problem of circulating current. The magnetic flux density is not uniform along the axis, which causes circulating currents to flow in the axial direction. And to minimize these errors, most workers recommend calibration for animal work by using blood from the animal and, where possible, the animal's own vessels also, with some related required also ethics. Blood or saline is usually collected in a graduated cylinder and timed with a stopwatch. Electromagnetic flow meters have a magnetic field, And this magnetic field needs a type of current to excite, to generate this magnetic field. We can use a direct and alternative current for generate the magnetic field. In other words, we can use two types of magnetic field, DC and AC. As you can see, direct current flow meters have been considered in this slide. The flow meter can cause a magnetic field, so the output voltage continuously indicates the flow. Although a few early DC flow meters were built, none were satisfactory for the following three reasons. If I ask you, say the reasons or the disadvantage of using DC flow meters, you should answer based on these three reasons. The first one is the voltage across the electrodes metal to solution interface is in series with the flow signal. It's important that the metal to solution half cell potential is also a DC voltage. Even when the flow meter has non-polarizable electrodes, we usually use a simple metal electrodes, and the random drift of this voltage is of the same order as the flow signal, and there is no way to separate these two DC voltage. The second reason is the ECG has a waveform and frequency content similar to that of the flow signal. Especially near the heart, at the vessels near the heart, the ECG waveform is much larger than that of the flow signal, and therefore cause significant interference. The third reason is in the frequency range of interest, 0 to 30 Hertz, we have a noise in the amplifier, and this kind of noise is large at low frequency region, at our low frequency region in this recording. Therefore, this bad effect leads to a poor SNR, signal to noise ratio. Because of the considered reasons, we usually use alternative current flow meters, and therefore we should have a complicated circuit to generate and record these types of voltage, but those problems, those disadvantages of DC flow meters are not present in this type of current flow meters. Okay, the clinician can eliminate the problems of the DC flow meters by operating the system with an AC magnet current of about 400 Hz. Lower frequencies require bulky sensors, whereas higher frequency cause problems due to stray capacitance, and therefore we choose this frequency. The operation of this carrier system results in the AC flow voltage shown in this figure 8.5. When the flow reverses direction, the voltage changes phase by 180 degrees. So the phase sensitive demodulator is required to yield directional output. And also, we should consider another problem. We should consider another problem about the direct we should consider the direct coupling or induction between sensors between coils in these types of magnetic flow meters. As I told you before, we have a direct coupling problem. Although AC operation is superior to DC operation, the new problem of transformer voltage rises. If the shaded loop shown in figure 8.3 referred to the book is not exactly parallel to the B field, magnetic field, some AC magnetic flux intersects the loop and induces a transformer voltage proportional to dB divided by dt in the output voltage. Even when the electrodes and wires are carefully positioned, the transformer voltage is usually many times larger than the flow voltage, as indicated in figure 8.5. The amplifier voltage is the sum of the transformer voltage and the flow voltage. And therefore, we should consider this problem. We should detect and separate this large voltage from the main EMF from the flow. There are several solutions to this problem. One, it may be eliminated at the source by use of a phantom electrode. One of the electrodes separated into two electrodes in the axial direction, and a potentiometer is placed between them. Note in figure 8.5 that we can sample the composite signal when the transformer voltage is 0. At this time, the flow voltage is at its maximum, and the resulting gated signal measures only the flow voltage. However, if undesired phase shifts cause the gating to be down even a few degrees away from the proper time, large error and drift results. The best method for reducing the effects of transformer voltage is to use the quadrature suppression circuit shown in Fig 8.6. In this slide, a perivascular probe in electromagnetic flow meter probes has been shown. As you can see, a toroidal laminated permalloy. Core is wound with two oppositely wound coils. We have a core and two wounded coils, oppositely wound coils here will generate our electromagnetic field. This structure is a specific structure. These probes comes in 1 millimeter increments for 1 to 24 millimeter diameter blood vessels. Also, individual probes cost $500 each, made to fit snugly to the vessel during diastole, because during the diastole the pressure inside the vessel is low, therefore we can fix it inside the probe. These probes only will use with arteries, not veins, as collapsed veins during diastole lose contact with the electrodes. Always we need to be connected to the electrodes. Because of the low pressure inside veins, especially during diastole, we will lose the connection between the electrodes and the wall of the vessel. Therefore, only we can use these probes to measure the flow rate inside the arteries, because of the high pressure inside the arteries and good connection between the walls and the electrodes of the probe to the vessel walls. Needless to say, this is an invasive measurement. We need to put the vessel inside this probe. Therefore, we need some invasive operations. A major advantage is that it can measure instantaneous blood flow, not just average flow. We can we have a continuous measuring, also instantaneous blood flow measuring using this type of flow meters.